Overview of Pandas. Pandas is a Python library used for working with datasets. It allows for data manipulation and analysis by providing data structures and operations for manipulating numerical tables and time series. The name Pandas is derived from the term panel data, an econometrics term for multidimensional structured datasets. In the provided code, we start by importing the Pandas library using the common alias PD. We then create a simple data frame, which is one of the primary data structures in Pandas. A data frame is similar to a spreadsheet or a SQL table and is optimized for various data analysis tasks. The data dictionary contains the data we want to organize, with the keys representing column names, name, age, city, and the lists corresponding to the column values. Finally, we use pd.dataframe data to create the data frame and display df to print the resulting table-like structure. Installing Pandas. Before using Pandas, you need to install it. Pandas can be installed using pip, which is the Python package manager. Ensure you have Python and pip installed on your machine before proceeding. The code pip install pandas is used in the terminal or command prompt. When executed, pip contacts the Python package index, PyPI, to download and install the Pandas package along with its dependencies. Once the process completes, Pandas is available for use. To start using it, you can import Pandas in your Python script with import pandas as PD. This step is essential before you can start manipulating and analyzing data using Pandas. Importing Pandas. To start working with Pandas in Python, you first need to import the Pandas library. This step is crucial as it allows you access to all the functionalities Pandas provides for data manipulation and analysis. The code import pandas as PD imports the Pandas library into your Python script, making its functions and classes available for your use. The as PD part of the statement is optional but commonly used. It allows you to use the abbreviation PD instead of pandas each time you need to call something from the library. This convention is widely adopted for brevity and convenience. Pandas data structures, series and DataFrames. Pandas is a powerful library in Python, widely used for data manipulation and analysis. At its core, Pandas offers two main data structures, series and DataFrames. A series is a one-dimensional array-like object capable of holding any data type, while a data frame is a two-dimensional table-like structure designed to handle a collection of series objects. In the provided code, we import Pandas with the alias PD, which is a common convention. We then create a series from a list of integers using pd.series 1, 3, 5, 7, 9. This series consists of 5 elements, each holding an integer. For the data frame, we construct it from a dictionary data, where each key is a column name and its associated value is a list of elements. This creates a data frame with 2 columns, column 1 and column 2, each containing 3 values. The data frame structure allows for data to be organized in a tabular form, enabling easy data manipulation and analysis. Understanding the Pandas documentation. The Pandas documentation is a comprehensive resource that explains how to use the Pandas library effectively. It includes explanations of Pandas' structures, functions, and various uses. Understanding how to navigate and interpret this documentation is crucial for learning and mastering Pandas. This piece of code is fundamental for anyone getting started with Pandas. First, we import Pandas under the alias PD, which is a common convention. Then, we use Python's built-in help function, passing in PD as the argument. This action will display the documentation for Pandas within the console or Jupyter Notebook environment. The documentation presented will include an overview of Pandas, its classes, and functions, along with brief descriptions of each. This is an excellent way for beginners to get acquainted with the vast features and functionalities Pandas offers right from their programming environment. Creating series and data frames. A series is a one-dimensional labeled array capable of holding any data type. Here's how you can create a series in Pandas. In this code, we first import Pandas with the alias PD, which is a common convention. Then, we create a series S by calling the PD_series constructor and passing a list of numbers as the data. The series S is then printed, showcasing its automatically assigned integer index alongside the values. Viewing data. In Pandas, viewing data is crucial for understanding the structure and content of your data frame or series. Starting with simple methods, you can inspect the first few rows, the last few rows, and the index, columns, and data types of your data frame. The provided code creates a data frame from a dictionary, then demonstrates how to use the head and tail methods to view the first and last two rows, respectively. This is often used to quickly check data without loading the entire dataset. Using head without specifying a number displays the first 5 rows by default, and similarly, tail defaults to the last 5 rows. Finally, using printdf.index, printdf.columns, and printdf_dtypes gives you an overview of the data frame's index, the names of the columns, and the data type of each column. These are fundamental for data exploration and integrity checks. Selecting data. In Pandas, selecting data is one of the basic operations that you'll perform quite frequently. Selection can be done in multiple ways, but 2 common methods are by using labels, column names, and positional indexing. Here, we use a data frame named data to illustrate these concepts. In the code provided, we perform 2 types of data selection. The first, using data A, selects all entries from the column labeled A. This method relies on using the column names or labels for selection. The second method, using data.illoc, selects all entries from the first row of the data frame. Here, illoc is used for integer location-based indexing, allowing us to select data by its position in the data frame, not by its label. Loading and saving data from to different file formats, CSV, Excel, SQL, JSON. Pandas provides convenient ways to read data from and write data to various file formats like CSV, Excel, SQL databases, and JSON. This functionality makes it easy to interchange data between different sources and Pandas data frames. The code demonstrates various ways to load and save data using Pandas. When reading CSV and Excel files, pd.read_CSV and pd.read_Excel are used respectively, with the file path as a parameter. For saving, to CSV and to Excel methods are applied on the data frame, specifying the file name. The parameter index equals false is included to prevent Pandas from writing row indices into the file. For SQL, an engine connection is first established using SQL alchemy, then pd.tsql manage reading and writing, with if exists parameter handling the behavior when the table already exists. For JSON, pd.readJSON and df.toJSON are used, with orient parameter in toJSON, specifying the format of the JSON output. Inspecting data for basic information, shape, info, describe. Pandas provides several functions to get a quick overview of datasets. Shape returns a tuple indicating the dimensions of the data frame. Info gives a concise summary including the data type of each column and non-null values. And describe generates descriptive statistics that summarize the central tendency, dispersion, and shape of a dataset's distribution, excluding and values. Here's how you use them. The df.shape command returns a tuple representing the dimensions, rows, columns of the data frame, helping you quickly understand its size. df.info offers a summary, including index data type and column data types, non-null values, and memory usage, vital for initial data assessment and cleaning processes. Lastly, df.describe provides a statistical summary for numerical columns by default, including count, mean, standard deviation, minimum, and maximum values, and quartiles, offering insights into data distribution and potential outliers. Together, these commands form a foundational toolkit for initial data exploration. Indexing and selecting data. Indexing and selecting data with Pandas involves various methods to access a subset of data from a data frame or series. These methods range from simple square bracket notation to more complex methods like lotloc, eloc, and Boolean indexing. In this example, the data frame df is created with data consisting of names, ages, and cities. To access the age column, use square brackets with the column name as a string, dh. This returns the age column as a series. To select multiple columns, such as name and city, a list of column names is passed inside the square brackets, df name, city. This returns a new data frame containing only the specified columns. Selecting data in this manner is straightforward and often used for its simplicity and readability. Data slicing. Data slicing in Pandas is used to select and extract specific rows or columns from a data frame. This is typically done using the loc and iloc accessors for label-based and integer-based indexing, respectively. Slicing can be very useful for extracting subsets of data for analysis. In the example code, we first import pandas and create a simple dataframe df with 2 columns, name and age. We then use iloc to slice the dataframe, selecting rows 1 through 3. Python uses zero-based indexing, so this actually selects the 2nd through 4th rows of the dataframe. The sliced portion is stored in sliced.df, which is then printed showing the selected rows. Boolean indexing. Boolean indexing in Pandas allows you to select data subsets from a data frame based on the value's truthiness. It's akin to filtering data by applying conditions directly to columns. For instance, to filter rows where a column's values meet certain criteria, you create a Boolean condition that, when applied to the data frame, returns a subset of it containing only the rows that satisfy the condition. Firstly, a Pandas data frame is created from a dictionary containing ages and names. To filter this data frame to include only those rows where the age is less than 30, we use Boolean indexing. The expression df_age30 generates a Boolean series that's true for rows where the age is less than 30 and false otherwise. When we use this series to index the data frame df_age30, Pandas returns a new data frame containing only the rows for which the condition was true, effectively filtering the data frame to our desired condition. Setting and resetting index. In Pandas, indexes play a crucial role in data manipulation and retrieval. Setting and resetting an index can help in organizing data more effectively. setIndex is used to set a data frame column S as the index, whereas resetIndex changes the index back to a default integer index. The code begins by importing Pandas. A data frame is created with name and age columns. df.setIndexName sets the name column as the index, shifting the default integer index to the side. This can be particularly useful for quick data retrieval using names. Later, df_set.resetIndex is applied to reverse this operation, bringing back the default integer index. This is helpful when the set index doesn't serve the analysis, or when you need to perform operations that require the standard numeric index. Handling missing data, dropna, fillna. In Pandas, missing data is often represented by nan, not a number or none. Handling missing data is crucial for preparing a dataset for further analysis or machine learning models. 2 common methods for dealing with missing values are dropna and fillna. Dropna allows you to remove rows or columns with missing values, while fillna enables you to replace them with a specific value, a method like forward fill or backward fill, or an interpolated value. The example starts by importing Pandas and creating a sample data frame df containing missing values, none. The dropna method is used to create df_dropna, a new data frame where any row containing at least one missing value is removed. Consequently, this could lead to a significant reduction in dataset size if there are many missing values. The fillna method is applied to create df_fillna, where all missing values in the data frame are replaced with 0. This method is useful for maintaining dataset size, but requires careful consideration of the replacement value to avoid introducing bias or inaccuracies. Renaming columns. Renaming columns in a Pandas data frame is a common task that helps in improving the readability of your data frame, making it easier to work with, especially when dealing with data from various sources which might not have meaningful column names. Fortunately, Pandas provides a straightforward way to rename the columns using the rename method. In this example, we start by importing Pandas and creating a simple data frame df with 2 columns labeled A and B. Each column has 3 entries. Next, we use the rename method on the data frame to change the column names. The rename method requires a dictionary where the keys are the existing column names and the values are the new column names. Here, we're changing A to alpha and B to beta. After renaming the columns, we print the updated data frame to verify the changes. The result is a data frame with the columns now labeled as alpha and beta instead of A and B. Data sorting and ranking. Sorting data is fundamental in any data manipulation process as it helps in understanding trends and making decisions. Pandas offers easy-to-use functions for sorting data frames or series. Additionally, ranking assigns ranks from 1 through the number of valid data points in an array. Let's dive into how sorting and ranking can be performed in Pandas with a practical example. In the provided code, we start by importing pandas and creating a sample data frame named df with two columns A and B. Using the sort values by equals A method, we sort df by column A in ascending order, resulting in a new data frame sorted df. For ranking, we call the rank method on column A directly, which assigns rank starting from 1. The print statements at the end display the sorted data frame and the ranking of column A. Sorting helps in reordering data for analysis, while ranking is useful for comparative analysis across a dataset. GroupBy operations. GroupBy operations are crucial for aggregating data based on categories or group labels. They enable powerful data analysis techniques, allowing us to summarize and analyze subsets of data within a larger dataset. The process typically involves splitting the data, applying a function, and then combining the results. In the example, we have a data frame df that includes a category column and a values column. We perform a GroupBy operation on df using the category column to define our groups. The .GroupBy category method groups the data by category. Following this, we apply the .sum aggregation function to each group, which sums the values within each category. The result is a new data frame grouped that displays the sum of values for each category. This process allows us to easily understand the cumulative behavior of the data within each group. Pivot tables and cross-tabulations. Pivot tables are a powerful feature in Pandas that allow you to summarize and aggregate data in a data frame to gain valuable insights. You can specify which columns to use as index, rows, columns, and the type of aggregation, sum, mean, etc. to apply. In this example, we create a data frame df with sales data for products A and B over 2 years. Using pivot table, we assign year as the index rows, product as the columns, and aggregate the sales data by summing it up. This structure helps in quickly understanding the total sales of each product per year. Data aggregation and summarization. Data aggregation and summarization are powerful Pandas techniques for transforming, rearranging, and summarizing your data to perform meaningful analysis. Using GroupBy, aggregate, and summarizing functions like mean, sum, you can condense large datasets into meaningful information. Let's explore these concepts with a practical example where we summarize sales data by calculating total sales and average sales price per category. In this example, we first import Pandas and create a data frame df with sample sales data including categories of products, their sales, and quantities. Using the GroupBy method on category, we organize the data by product category. The agg method allows us to perform multiple aggregation operations simultaneously. Here, we calculate the total sales by summing up sales within each category using sum, and average sales by calculating the mean sales price using mean. Finally, reset index is used to convert the index category back to a column, making our data structured and easier to read. This method efficiently summarizes our sales data by category. Merge, join, and concatenate data frames. In Pandas, merging, joining, and concatenating are powerful ways to combine data frames based on their index labels or columns. Merge is used for combining data frames using database-style joins. Join connects data frames based on their indices, and concatenate sticks data frames together along a particular axis. In the code example, pd.concat df1 df2 axis equals 0 concatenates df1 and df2 vertically, since axis equals 0, which means it stacks one on top of the other, appending df2's rows to df1. The function pd.merge df1 df2 on equals a merges df1 and df2 horizontally based on the common column A, effectively performing an SQL-like join. The on parameter indicates the column S on which to align the data frames. In this case, where column A values are unique in each data frame and appear in both, merge finds matches between these columns to combine the data frames. Working with time series data. Pandas is exceptionally useful when dealing with time series data due to its dedicated datetime data types and accompanying methods. Time series data often comes in the form of dates and times, which we can manipulate and analyze using Pandas. A common operation is converting strings to datetime objects and then performing analysis, such as resampling the data to get daily means. This example creates a simple data frame with a date column and a numeric value column. First, it converts the date strings into datetime objects using the pd.toDateTime function. which is crucial for time series operations, as it allows Pandas to recognize these as date objects. Then, it sets the date column as the index using setIndex, which is a common practice for time series data, facilitating operations like resampling. Resampling is demonstrated with .resampleD.mean, which calculates the daily mean of the values. This process of converting, setting the index, and resampling is foundational in working with time series data in Pandas. Handling categorical data. In Pandas, categorical data is often represented using category D-type. Handling categorical data efficiently is crucial because it can lead to performance improvements and easier data analysis. This entails converting text labels into a numeric form, managing categories, and properly visualizing categorical data. In this example, we first import Pandas. We then create a Pandas series named Data with some categorical data, low, medium, high. We explicitly define the data type as category when creating the series. Next, we reorder the categories using data.cat.setCategories and set them as ordered. It's important to define the order of categories when it has an intrinsic order, low, medium, high. Lastly, we display the categorical data and their corresponding encoded numerical codes using data.cat.codes. Numerical codes are useful for machine learning models that require numeric input. Vectorized string operations. Pandas provides powerful string operations that allow for fast, simple, and convenient manipulation of text data. These operations are vectorized, meaning they are optimized to operate on entire arrays of data without the need for explicit loops. This capability is particularly useful when working with large datasets containing text information. Here, we'll explore how to perform basic string operations on a Pandas series. In this code, we first import Pandas and create a series object named data containing various text values. The .stir accessor is used to access vectorized string methods, allowing for operations over each element in the series. Here, .upper is called via .steerer, which converts all characters in each string to uppercase. This operation showcases how to apply a simple text transformation across an entire Pandas series efficiently without needing to loop through each element. The result is a new series where all text has been transformed to uppercase. Working with text data. Pandas provides a powerful set of methods to process, transform, and manipulate text data in series or data frame objects. These methods enable efficient cleaning and transformation of text data for further analysis or visualization. We will explore some common text operations such as string casing, splitting, and replacement. In the provided code snippet, we import the Pandas library and create a data frame named df containing names of individuals. We then demonstrate two common text processing tasks, converting text to lowercase and splitting text into multiple columns. The .str.lower method is used to convert all the names in the name column to lowercase. Subsequently, the .str.split expand equals true method is applied to split the names into first and last names using a space as the delimiter. The expand equals true parameter instructs Pandas to split the names into separate columns, resulting in a new data frame with first name and last name columns. Applying functions to data, apply map. Pandas provides several methods to apply functions to data, allowing for complex data transformations and analysis. Apply is used on series and DataFrames for applying a function along an axis. Apply map is data frame specific, applying a function element-wise. Map is used with series to substitute each value with another value. The code demonstrates the use of apply map, and map methods in Pandas. df.apply lambda x 2 doubles each element in the data frame, demonstrating apply's usage on a data frame. df.apply map lambda x plus 1 adds 1 to each element, showcasing apply map for element-wise operation on data frames. Lastly, dfa.map lambda x squares each element in column A, exemplifying how map is used to transform series data by applying a provided function. Multi-index and advanced indexing. A multi-index, or hierarchical index, in Pandas allows you to have multiple index levels on an axis. This is useful for working with high-dimensional data, enabling you to elegantly and efficiently handle data in a more structured way. Let's create a simple data frame with a multi-index to demonstrate its basic functionality. In this example, we import Pandas and define two lists that represent our index levels, We then create tuples from these lists, which are used to form a multi-index via pd.multiindex.fromTuples. This multi-index serves as the index for our data frame, df. Each row can be uniquely identified by a combination of the first and second index levels. The printed output is a data frame with a hierarchical index, where bar and baz are the top-level indices, and 1 and 2 are nested within them, with each combination corresponding to a row in the data frame. Pivoting and reshaping data. Pivoting and reshaping data in Pandas allows you to transform or restructure your data in a manner that makes it more understandable or easier to analyze. We'll explore methods like pivot, melt, stack, unstack, which are crucial for wide to long format transformations or vice versa. In the code, 2 Pandas techniques for reshaping data have been demonstrated. First, pivot is used to turn the data frame into a wide format where rows are labeled by unique dates, columns by unique type, and cell values are value contents. This is helpful when analyzing or comparing different categories over time. Second, melt is applied to transform the data frame back into a long format where each row represents a single observation, making it suitable for detailed data analysis or further transformations. ID vars specifies columns to retain, not melt, while value vars lists columns to melt into the long format. Plotting directly with Pandas. Pandas provides convenient methods for data visualization, which allow for quick and efficient plotting of data directly from a data frame or series. This is possible through an integration with MapPlotLib. To use this functionality, one must first ensure MapPlotLib is installed. In this example, we will create a simple line plot from a Pandas data frame. In the provided code, we first import the required libraries: Pandas for data manipulation, NumPy for numerical operations, and MapPlotLib for plotting. Then, we create a data frame df with 2 columns, A and B, each containing 10 random numbers generated using np.random.rand10. The plot method is called directly on the data frame to create a line plot. The kind parameter specifies the type of plot, in this case line. Finally, plt.show displays the plot. Plotting directly from Pandas like this makes it convenient to visualize the trends and relationships in the data without significant boilerplate code. Customizing plots. Pandas plotting is built on MapPlotLib and provides a simple way to plot data frame and series objects. Customizing these plots allows us to make our visualizations more informative and appealing. We'll focus on customizing a simple line plot. In this code, we first import the necessary libraries: Pandas for data manipulation, NumPy for numeric operations, and MapPlotLib.pyplot for plotting. We create a sample data frame df with 2 columns A and B, each containing random values. Using the plot method, we customize our line plot by setting the figure size with fig size, adding a title, enabling the grid for better readability, and customizing line styles and colors for each column. A is styled with red dashed lines, while B is styled with green lines and circle markers. Finally, we explicitly label the x-axis as index and the y-axis as values to make the plot informative. Pandas integration with MapPlotLib. Pandas provides direct integration with MapPlotLib, allowing for quick and easy visualization of data frames and series. This integration facilitates the creation of plots directly from Pandas objects, leveraging MapPlotLib's plotting capabilities. Visualizing data is crucial for understanding underlying patterns and making informed decisions. In this example, a Pandas data frame is created from a dictionary containing year and sales data. Using the plot method on the data frame, we specify the columns for the x-axis, year, and the y-axis, sales, and choose the kind of plot as bar to create a bar chart. The plot method internally uses MapPlotLib to generate the plot. Then, plt.show is called to display the plot. This code snippet showcases how seamlessly Pandas and MapPlotLib work together to visualize data. Plot types: line plots, bar plots, histograms, box plots, scatter plots. Line plots are useful for showing changes over periods of time. They can also be used for comparing changes over the same period for different groups. This code snippet creates a simple line plot using MapPlotLib. The x-axis represents the year, and the y-axis represents sales. The pl.plot function is used to generate the line plot. Titles and labels are added with plt.title, plt.xlabel, and plt.ylabel to make the plot more informative. Using Cborn with Pandas. Cborn is a Python data visualization library based on MapPlotLib that provides a high-level interface for drawing attractive statistical graphics. It integrates well with Pandas, allowing us to leverage DataFrame objects directly to create visualizations. We'll start by visualizing distribution of values within a column using Cborn's sns.histplot. In the provided code, we import the necessary libraries, Cborn for plotting and Pandas for handling data in DataFrame format. We create a simple DataFrame df with a single column age containing various age values. Using sns.histplot, we plot a histogram of the age data. The KD equals true argument adds a kernel density estimate KDE plot on top of the histogram. This combination provides both a discrete representation of data frequencies through the histogram and a smooth estimation of the data distribution via the KDE plot. Query and eval functions for efficient operations. The query and eval functions in Pandas offer a more efficient way to perform operations on data frames. They use string expressions to efficiently compute operations using DataFrame objects. This is particularly useful for large datasets, as these methods can be faster than traditional methods and can reduce memory usage. In the given code, we use eval to create a new column C in df by adding columns A and B. The in-place false argument creates a new data frame with the result without modifying the original df. Then we use query to select rows where column A is greater than 3. Query is beneficial for filtering rows based on a condition expressed as a string. Both methods utilize string expressions, making it easier to write and read operations, especially for complex conditions or calculations. Using categorical data type for memory efficiency. The categorical data type in Pandas is useful for storing data that can take on a limited, fixed number of possible values, categories, such as days of the week. Converting a string column to a categorical type can drastically reduce memory usage, which is pivotal for enhancing performance, especially with large datasets. Here's how to do it. The code creates a data frame with a column day repeating days of the week. Initially, the column day is of object type, strings, which is memory intensive. By converting it to a categorical type using .astype category, each unique string value is internally represented by a much smaller integer, and this mapping significantly reduces memory usage. The memory usage deep equals true method is used to calculate the total memory used by the data frame before and after conversion, illustrating the efficiency gained with categoricals. Optimizing performance. When working with Pandas, optimizing performance is crucial, especially with large datasets. One key approach is using vectorized operations instead of iterating over data frame rows. Let's consider calculating the square of each number in a data frame column. This code demonstrates the efficiency of vectorized operations in Pandas. By avoiding explicit loops to square each number in column A, we utilize Pandas' internal optimizations, significantly speeding up the computation. The operation dfa2 efficiently computes the square of each element in the column and stores the result in a new column, A squared. This approach is much faster and more readable than iterating through rows. Parallel processing with Dask. Dask offers parallel computing in Python, efficiently running large-scale computations. It works well with NumPy, Pandas, and scikit-learn. For Pandas users, Dask DataFrame provides a familiar interface for out-of-core and parallel computing, ideal for datasets too large to fit into memory. In this example, we first import Dask's DataFrame module. We then load a large CSV file into a Dask DataFrame, which doesn't immediately read the entire file into memory, instead preparing to process it in chunks. Next, we perform a GroupBy operation, which is executed in parallel across the dataset. The compute method triggers the actual computation, efficiently utilizing available CPU cores. This example showcases Dask's ability to handle large datasets by partitioning data and parallel processing, extending Pandas' capabilities. Data cleaning and preparation. Data cleaning and preparation is a critical step in any data analysis project. It involves identifying and correcting errors, handling missing values, and formatting the data to make it suitable for analysis. In the context of using Pandas, a popular Python library for data manipulation, we'll go through some common data cleaning tasks. In the code snippet, we start by importing Pandas, and creating a data frame with some purposefully missing values. Missing data can disrupt many types of analysis, and it's common to replace these missing values with placeholder values. For string fields, we might use a placeholder like unknown, whereas for numeric fields, we might use the mean or median of the column, which are more representative of the dataset, compared to filling with 0 or dropping rows columns outright. The .filner method is very versatile, allowing us to specify what values to fill in for missing values on a per-column basis by passing a dictionary to the method. Using in-place equals true applies the changes directly to the data frame without needing to assign it to a new variable. Exploratory data analysis, EDA. Exploratory data analysis, or EDA, is an approach to analyzing datasets to summarize their main characteristics, often with visual methods. EDA is crucial for understanding the underlying structure of data, spotting outliers and anomalies, and finding interesting patterns that warrant further study. Pandas, along with visualization libraries such as MapPlotLib or Cborn, makes EDA very intuitive and powerful. Below is an example of a simple EDA process using the Pandas library. The code begins with importing the Pandas library, essential for handling data in Python. It then reads a CSV file, sampledata.csv, into a data frame, which is a two-dimensional labeled data structure with columns of potentially different types. The df.head function displays the first 5 rows of the data frame, providing a quick glance at the data and its structure. Following this, df.describe generates descriptive statistics that summarize the central tendency, dispersion, and shape of the dataset's distribution, excluding NaN values. Finally, df.asnull, sum, is used to identify and count any missing values in each column, which is crucial for data cleaning and preparation before further analysis. This process outlines the foundational steps in EDA, offering insights into the data's quality and structure. Building a data pipeline with Pandas. A data pipeline is a series of data processing steps that aim to transform and transport data from a source to a destination. Building a data pipeline with Pandas involves loading data, performing transformations, and exporting the processed data. Here we illustrate this with a simple example, where we load data from a CSV, filter rows, add a new column, and then save the processed data to a new CSV file. The code starts by importing Pandas, which is essential for data manipulation. Then, it loads data from a CSV file into a data frame. Next, it filters the data frame to include only rows where the age column value is greater than 18. This is achieved using a condition inside the square brackets. After filtering, a new column adult is added to indicate that these filtered individuals are over 18, assigning true to each row. Finally, the processed data frame is written to a new CSV file, excluding the index with index equals false, as this may not be necessary or meaningful in the new file. Case studies: financial analysis, time series forecasting, machine learning data preparation. In this case study, we'll explore how to perform basic financial analysis using Pandas. Specifically, we'll calculate the daily return of a stock. The code snippet provided demonstrates how to calculate daily returns of a stock using Pandas. It starts by creating a data frame with stock prices over several dates. The date column is converted to datetime and set as the index for easy time series manipulation. Then, the percentage change between each day's stock price, AAPL column, is calculated using the PCT change method, producing the daily return. This basic financial analysis technique is crucial for assessing stock performance over time. Analyzing a dataset of choice. In this project, we'll analyze a dataset containing information on movies from the MovieLens database. We will focus on understanding the average rating for each movie, showcasing fundamental data manipulation and analysis techniques using Pandas. First, we import Pandas for data manipulation. Next, we load two CSV files, movies.csv containing movie information and ratings.csv with user ratings for these movies. We merge these two datasets on the movie ID column to connect each rating with its corresponding movie. Then, we group the merged dataset by movie titles and calculate the mean rating for each movie using the mean function. Lastly, we print the first few records of the average ratings to get a glimpse of our results. This process helps us understand how viewers rate different movies and identify high or low-rated movies.